I'm sorry, Dave. I'm afraid I can't do that.
Coordinate geometry. Now, this video is a little bit long, so feel free to pause it at any point, come back to it later, take a couple breaks, but I'm going to go through it as quickly as I possibly can. First of all, there's three formulas related to coordinate geometry that you need to be familiar with. The most important of which are the midpoint formula and the slope formula. Now, keep in mind this slope is basically a measure of the slantiness of a line, and this change in y over change in x basically represents how the x and y values have changed. So I have y2 minus y1. It represents the change in the y values. x2 minus x1 represents the change in the x values, and that's between 2 points, x1, y1, and x2, y2. So for any 2 points, I could determine the slope by taking the difference of the two coordinates, and it's the ratio of the changes in y's over the changes in x's. For the midpoint is basically the average coordinate. It's the sum of the x values of those 2 points and the sum of the y values of those 2 points divided by 2. Distance formula also deals with changes in x and changes in y, and if you recall, it actually came from the Pythagorean theorem. Now, a couple properties of lines. Parallel lines have slopes which are equal to each other. Perpendicular lines have slopes which are negative reciprocals of each other. That means that if I have a line with a slope a over b, that's the slope of one line, then the slope of a perpendicular line would have to be negative b over a. So it's a reciprocal, and it's the negation, or has the opposite sign of the other. Now, applying these to an example, say I want to find the midpoint distance and slope of AB given these 2 points. Well, the first thing I can do is find the change in y over the change in x. Now, a quick and easy way to find the change in y is to look at how things have changed from one point to the other. So my change in y values here have increased by 4, and my change in x values from this point to this point have decreased by 3, because I'd have to subtract 3 from 2 to get negative 1. I'd have to add 4 to 10 to get 4. So that's a quick way to find your changes in y and changes in x's without actually having to write out a large formula. With that in mind, I can quickly find the distance, which is the square root of this change in x squared, which would be 9, plus the change in y squared, which would be 16. So this is really the square root of 25, which is just 5. So there's my distance, 5. I can find my slope, which is the change in y, which is positive 4, over the change in x, which is negative 3. And whenever we have negatives in fractions, we'll pull them out. So negative 4/3 would be the slope. And finally, if I want the midpoint, which is usually represented with a capital M, is the average of these points. So it's no longer the change in y and the change in x. It'll be 2 plus negative 1, 2 plus negative 1 over 2, the average of the x values, and then the average of the y values, which will be 10 plus 14 over 2. Okay, so that point is really equal to, well, 2 plus negative 1 is 1, and 1 divided by 2 is 1/2. So that would be 1/2. 10 plus 14 is 24, divided by 2 is 12. So there's that midpoint. A circle, equation of a circle, is basically standard form x minus h squared plus y minus k squared is equal to r squared, where the center of the circle is hk and the radius is r. Notice that these coordinates, the x and y coordinate for the center of the circle, is opposite signs from those given in the equation. So a couple of examples here. Notice that we'll do B first. My center will be positive 1, opposite signs from this, and negative 3, opposite signs from this. So it has an x coordinate of 1 and a y coordinate of negative 3, and since this is the radius squared, the radius would be equal to the square root of 16, which is 4. Now I'll go back to the first one. Since I'm not subtracting anything from the x's or the y's, my two coordinates to represent nothing is basically 0, 0, so that's my center. And it has a radius squared of 100, which means the radius itself is just 10. Now, applying these formulas to polygons. So here's applications to polygons. Here's a couple properties of each of these special types of quadrilaterals. We have parallelograms have opposite sides that are parallel, opposite sides are congruent, and the diagonals bisect each other. And a rectangle is basically a parallelogram with 4 right angles. It's also true that if a parallelogram contains 1 right angle, then it would have to be a rectangle. Also, rectangles have congruent diagonals. A rhombus is another special type of parallelogram that has all congruent sides, so all 4 sides are congruent, and the diagonals are perpendicular to each other. There's one that's not listed here, which is a square, which is basically a combination of all the properties of a rectangle and a rhombus. So how does this stuff apply to coordinate geometry stuff? Well, say I have a quadrilateral with these 4 vertices, and I'm curious what type of special quadrilateral, if any, it would be. Well, I can start this off by kind of just looking at the slopes of each of the 4 sides. So I'll look at the slope of AB, I'll look at the slope of BC, I'll look at the slope of CD, and finally the slope of AD. So I'm going to look at those 4 slopes. It's the slope of each of the 4 sides, and I'm going to see if it follows one of those special patterns we look at. Recall, the parallel lines have equal slopes, perpendicular lines have negative reciprocal slopes. So I need the change in y and change of x. So I'm going to look at the changes in y's. I'll write it down for the first one to remind you how I find it. The change in y here, and then the change in x here. Okay, so the change in y has increased by 5 units from 0 to 5, and it has decreased by 1 unit from 0 to negative 1. So that gives me a slope of 5 over negative 1, which is just negative 5. So that's my first slope. Now you can repeat this process for each of them. So I encourage you to go through it and try it yourself, and then check yourself before you wreck yourself on this example. And I'm going to just fill in the solutions for each of these slopes so that we could get to the meat and potatoes of what it's all about. So when you find each of these slopes, trust me that you'll get 1/5, negative 5, and 1/5 for each of these slopes. Again, you go through that same calculation process we did for the first one. And now, based on this information, I can make a couple of conclusions. Well, since AB and CD both equal negative 5, I can conclude that line AB, or segment AB, I should say, is parallel to segment CD. And also, since BC is 1/5 and AD is 1/5, I also know that BC is parallel to AD. Well, 2 sets of parallel sides make the shape a parallelogram, so I have a parallelogram here, ABCD. Now my question would be, is it either of these 2 special parallelograms, either a rectangle or a rhombus? Because those are both also parallelograms. So now notice that this AB is negative 5, BC is 1/5. Well, since those are negative reciprocals of each other, it must also be true that AB is perpendicular to BC. So this is basically a parallelogram with 1 right angle, which makes it a rectangle. Because a parallelogram with 1 right angle is a rectangle. So I know what it is, and this is the reason why it is. So that's how you can use these 3 formulas, midpoint, slope, and distance. I actually only had to use the slope here, but there's multiple ways to prove each of these things. I could have used the diagonals, showed that the diagonals share the same midpoint. That would show it's a parallelogram, and then show the diagonals are congruent to show it's a rectangle. If it turned out the diagonals were perpendicular, it would have been a rhombus, but this is basically the process I would go through to determine what kind of shape I have. So the other kinds of things that we did with coordinate geometry was writing the equations of lines. Well, there are 2 special kinds of lines. Vertical lines, which have undefined slopes, and that's basically when all the x coordinates are the same. So x equals 3 would be the vertical line where all of the x coordinates were 3. So it would look something like this. So here's the line x equals 3. Here's my y-axis and my x-axis. So it would look something like that. Horizontal lines are when the slope is 0, so it's not rising at all. So what that would look like, an example would be y equals negative 1. So that would be the horizontal line that passes through all the y coordinates being negative 1. Okay, so that's an example of that. And then we have diagonal lines. Now, the main thing that's different between horizontal and diagonal lines is that diagonal lines have a particular slope. So it has a particular slantiness to it that I have to account for. There are 3 forms of diagonal lines. This is the slope-intercept form, because I can read off the slope, which is m, and the y-intercept, which is b. Okay, so it passes through the y-axis at the value b in the first type of line. The second one is point slope, because I can read 2 things off of this equation, the line. One is a point that's on that line, which is x1, y1, or the coordinates of 1 point on that line, and again, the slope, which is m. Now the last form is standard form, and what's very inconvenient about standard form is that I can't really read off any crucial information. However, I am able to graph this rather quickly, and we'll see how in just a minute. Okay, so now if I want to write the equation of a line, if it's one of the two special lines, vertical or horizontal, I'm just going to use those x or y coordinates. And if it's a diagonal line, I'm going to use one of these three forms, and I'll specify the form that you should be writing it in. So if I want to write the equation of the line containing these 2 points in slope-intercept form, that's y equals mx plus b. I'm going to have to get it in this form for my final answer. The first thing I'm going to need to know is my slope. Well, conveniently, I can use slope formula to figure that out when I have 2 points. So again, I'm going to need my change in y, which from 4 to 6, my change in y has gone up 2 units. I've increased by 2. And from 2 to 5, my change in x has increased by 3. So my slope, which is my change in y over my change in x, will be 2 over 3. So I know my slope. And since I know, in fact, 2 points on this line, the most convenient form of the line to start with would be point slope, because I know a point and I know the slope. So I'd be able to start off with a point slope form. So that's, where'd my pen go? There we go. Y minus y1 equals the slope times x minus x1. Well, the point I'm going to use for this line is the point 2, 4. You could equally use 5, 6. It would be just as equivalent. We actually end up with the same form at the end. But it'll be y minus the y coordinate of that point, which is 4, is equal to m, which is the slope, which we know to be 2/3, times x minus the x coordinate of that slope, which is 2 in this case. So now I'm going to distribute this 2/3 through this, or actually, one thing I forgot to mention, about the standard form, I'm just going to go back for 1 second, is that these a, b's, and c's have to be integer values, and the value a cannot be negative. So that's one thing to note. Okay, so now going back to this example, make sure you note that. I'm going to distribute this 2/3 to this example. So I get y minus 4 equals 2/3 x minus, and 2/3 times 2 would give me 4/3. I'm going to add 4 to both sides. So I end up with y equals 2/3 x, and then if I add 4 to 4/3, if I add 4 to negative 4/3, that's subtracting 1 1/3 from this. So that'll give me plus, 2 and 2/3, and we don't like to write things as mixed numbers, so I'm going to write that as a improper fraction, which will give me 2 times 3 is 6, plus 2 give me 8/3. Okay, so I get 2/3 x plus 8/3. That's my final answer. Okay, moving down. Write the equation of a vertical line through the point 1, 5. Well, if it's vertical, that means straight up and down, which means my x coordinates will never be changing. So I can best represent that since my one point on this line would be 1, 5, and I never change in my x values. I could represent that by x equals 1 would be my vertical line. Write the equation of a line containing these 2 points. The third one, now what's very convenient about this is that this, when x is 0, this is actually the y-intercept of the line. So I can write this in, I could start this off with slope-intercept form, and I eventually have to get it into standard form. Okay, so that's my standard form that I have to get it into, but I'm going to start off with y equals mx plus b, which is slope-intercept, because I know the y-intercept, and I can determine the slope by, again, change in y. I've increased by 3, change in x. I've increased by 2. So my slope here is 3/2, so y equals 3/2 x, and the intercept for y is 5 plus 5. It's my starting line. Now if I want this in standard form, I have no fractions, so what I'm going to do is multiply this entire equation by 2 to get rid of my fraction here. I end up with 2y equals 3x plus 10. When I distribute that 2 to every term, and I'm going to bring x to the other side, and I get negative 3x plus 2y equals 10. But recall, I can't have negative numbers as my leading coefficient here, so I'm going to multiply everything by negative 1, and I get 3x minus 2y is equal to negative 10. So there's my final standard form. No fractional coefficients, and my leading term is positive. Now, graphing lines. Horizontal and vertical lines, those are pretty straightforward to graph. Vertical lines straight up and down, horizontal lines left to right. Diagonal lines, in order to graph them, you need to know 2 things. You need a starting point and a direction. Now the direction can be given to you in one of 2 ways. It could be a second point, or it could be the slope. So we're going to look at a couple of examples of graphing each type. So first off, I'm going to zoom out a little bit so we can see this whole value. Okay, so I'm going to graph first my initial line, which is x equals 2. Well, that's a vertical line through the coordinate x equals 2, so it's the line where all of the x coordinates are 2, so that would be this line. Now I'm going to highlight that in a particular color so it stands out, and I'll color code each of these. So we'll start with this one as, let's go with blue. So there's my first line. Now, a couple of things you should do is you should definitely include arrows on either end. So I'm going to put arrows on both of mine. So it has arrows on either end because I know it continues forever, and you should also label it. I'm just going to color code mine in the interest of time. Now, second one. This is neither a vertical nor horizontal line, so I'm going to need two things. First, the most convenient way to graph this, since it's in standard form, is to plug in 0 for x and get the y-intercept, and then plug in 0 for y and get the x-intercept. Notice if I plug in 0 for x, this will disappear, and I'm left with y equals 5, which means that when x is 0, y is 5. So that's 1 point on this line. I could do the exact same thing in reverse to get a value for y, and if I plug in 0 for y, so that would be all along the x-axis, the x value will be 5. So 5, 0 is another point on this line. So now when I go to draw it, I have a line which goes through these 2 points. Okay. Continues infinitely in both directions, so I'm going to add arrows to both sides. Arrows. And I'm going to color code it to the color that I was drawing in. Okay. So there's B. Again, you should always label. In fact, I'll label this one so that it stands out. This is x plus y equals 5. In fact, I'll go back and label the first one too. This is x equals 2. So there are my two labels, and there are my two lines. For C, again, I have a standard form line, so I can repeat this exact same process. When I plug in 0 for x, I'll get negative 2y equals 2, and when I divide both sides by negative 2, y would be negative 1. So 0, negative 1 is 1 point on this line. Now I'm going to go back and repeat the same process by plugging in 0 for y. Okay, so when I plug in 0 for y, this value will disappear, and I get x equals 2. So x equals 2 is a point on this line, and now I can connect those 2 points and draw my line. Let's see. Okay, there we go. Again, I'm going to add arrows to both sides. And I'm going to color it so that it stands out. And I'm going to label it. So this is x minus 2y equals 2. And the last one, y equals negative 7. Well, that's just a horizontal line. So at negative 7, my value for y is never changing, so there's my horizontal line. Again, I'm going to add my arrows to both sides, and I'm going to color code it. So let's go with purple for that line, and I will label it as y equals negative 7. Now, I want to point out one other way that you could have graphed the red line. So I'm going to delete it, and I'm going to graph it again. Okay. So had you wanted, you could have converted line B into slope-intercept form by subtracting x from both sides. So another way of writing it is y equals negative x plus 5. Well, notice that gives me my y-intercept is 5, so I know that's my starting point, and I know my slope is negative 1. Well, since slope is changed in y over change in x, that means I will go down 1 in the y direction when I go over 1 in the x direction. I go down 1 in the y and over 1 in the x. You could also think of that as going back 1 in the x and up 1 in the y direction. So when I connect all those points, I end up with the exact same line. Okay, and again, I'll color it the same color and add my arrows. Okay, so two ways of graphing this line. When it's in standard form, it's easier to plug in a value, find the x and y intercept. You could also convert to slope-intercept form, use the intercept and the slope. Now, solving systems of equations. There are three possible outcomes whenever you're solving a system of equations. You can either have no solution, one solution, or infinitely many solutions. Now, the three situations where this occurs, you'll have no solution if the lines are parallel. You'll have one solution if you have a unique point of intersection. So I'm going to write POI for point of intersection. That's when you have the one solution. That point of intersection is the solution. And when you have infinite solutions, if they turn out to be the same line, those lines actually are two ways of writing the exact same expression, you will get infinite many solutions, which is pretty much every point on the given line. So there are two ways to solve a system of equality, to see a system of equations, to see what its solution is. We're going to go through both of them rather quickly, solving graphically and solving algebraically. So first off, I'm going to graph both of these lines. So the x plus y equals 3, since that's in standard form, the quickest way for me to graph it is, again, the intercepts method. So I plug in 0 for x. So when x is 0, y will equal 3. That's 1 point on this line. I'm going to now erase that and repeat the same process for y. When I plug in 0 for y, I get x equals 3. So I know this is another point on that line. I'm then going to connect those 2 points with a line. Move it down a little bit. Okay, so there's my line. Let me just clean it up a little bit. It seems to be slightly off. There we go. Okay, and I'll add my arrows to both sides, and I am going to color code it. Okay, last thing I need to do is label it. So I'm going to label that. That was equation x plus y equals 3. So there's my first line. The next thing I need to do, graph my second line. So I'll do that in, let's go with blue. So notice this is in a different form. It's not in standard form. So what I'm going to do instead is graph this, since it's in slope-intercept form. I can read off the slope and read off the y-intercept. I'll start by plotting the y-intercept, my starting point, which is 6. And since my slope is 2, that means I go over 1 in the x direction, up 2 in the y. Well, notice that it's going to put me off the graph. So instead, what I can do is go down 2 in the y direction and over 1, or so I should say back 1 in the x direction, back 1 in the x and down 2 in the y. Okay, so that's going to give me my line. Connect those points. Oops, there we go. I'm going to color code that line. It should be blue, and it should have arrows on either end. After I do that, I'm just going to label it. That is y equals 2x plus 6. Now notice that since the slope of this line was positive, I get a line which slopes up. Since this line slopes down, I would expect its slope to be negative. And then the last thing I need to do solve graphically is identify my point of intersection. This is a situation where I have exactly one solution, and it is right here at the coordinates -1 in the x and up 1, 2, 3, 4 in the y direction. So -1, 4 is my point of intersection graphically. Now, rather than graphing, we could have also solved that system algebraically in the following way. Recall we went over two methods, by elimination and by substitution. And if we look at this equation, this set of equations, the quickest way to do this one is actually going to be by substitution, since I have a variable already isolated. So what I'm going to do is take this value for y and substitute it into my original equation. So my original equation is x plus y, but I know y is equal to 2x plus 6, so I'm going to replace that with that value. Equals 3, which means that 3x plus 6 equals 3, which means that 3x equals -3, and that x is -1. So now that's the x coordinate of my point of intersection. And if I want the y coordinate, I'm going to take that and substitute it back into my second equation. So I get y is equal to 2 times -1, which is this x coordinate I'm plugging in, plus 6, which means that y is -2 plus 6, which would be 4. So my point of intersection is -1, 4. Now notice, regardless of which method I got, I still got the same point of intersection. So you have those two methods, algebraically and graphically. You should be familiar with both.
And to make a long story short, too late.